As she told me, I'm a synthetic chemist. So here shows the research summary of my group. So our research is basically synthetic organic chemistry aimed at the construction of new functional pi conjugated other systems. So namely the development of the new synthetic reactions that can give the other containing pi conjugated functional molecules that are otherwise difficult to synthesize. And the other is aimed at the construction of chiral molecules based on the transition metal catalysis reactions. And recently we are very interested in the utilization of hydrogen bonding formation for the organic catalysis. Okay, so today I'm going to show you the TADF molecules using based on the development of new organic reactions. So probably thanks to him, I can skip the background of the TADF or the importance of the TADF molecules, almost the same as him. So as you know, the fluorescence is a very rapid process of the light that comes from the excited singlet state. When the energy difference in singlet and triplet state is very small efficiently, so the system processing can proceed drift-free, and also the reverse in the system crossing distance also this speak is very effective. So from this state, we can obtain the negative fluorescence. So as he said, there's a very demanding applications of the TADF molecules in the ORF devices, also materials, and also in the centers. So especially in the ORF devices, the electron and hole they combine to generate triplet singlet cytons in 75% and 10-5% respectively. So, however, usually with conventional fluorescent molecules, with the DST maybe 0.5 to 1 volt, only the singlet state comes to emit the light. It's a fluorescent, but however from the triplet state, it is deactivated in the narrow conversion. So it's important to utilize the triplet state, or I can say we have to manage the triplet state as the light source in all the devices. To do so, we can utilize the phosphorescence or TPA that he also will have explained. So I can skip. So TADF is of course a very efficient strategy for enhance the quantum efficiency of the ORF devices because you can utilize the 75% generating the 75% triplet state to convert to the emissive singlet state in principle, but it's very difficult. So in 2012, Professor Adachi in Kyushu, they demonstrated that the highly twisted non-axial structure molecules can allow for the efficient the RISC process to give the delayed fluorescence by thermal process. So as you can see here, the delta EST is proportional to the exchange energy. It's proportional to the homological overlap integral term. So in this equation, we indicate that if when you separate the HOMO and the HODUMO, usually being separated, such compounds can emit the TADF. So actually, in this molecule, the HOMO and the effectively separate and gives a very small density value and external quantum efficiency is very high, not higher than the theoretical maximum value of conventional fluorescent or 5%. So far, so Adachi's group developed so many donor acceptor twisted donor acceptor compounds materials for OLED devices ranging from blue to green and yellow. So they demonstrated many structures as emitting materials. But there are a few examples on the orange to red, so namely the low energy engagement lighting on TADF materials, various cars. Because one of the reasons why there are a few examples should be the excited states of this compound it will be deactivated following energy load. In addition, we are very interested in the development of new acceptor. So there are many selections of donors like aromatic diamines and like this and this one. So many donors are there. But regarding the acceptor, there is a few several acceptors. But we think we thought if we could develop the new acceptor, it's how to say very gives a impact on the principle of molecular design. So on the other hand, as I told you, I am a synthetic chemist. So from the viewpoint of the synthetic chemist, if we could develop a new organic reaction that can allow for the access to the unprecedented structure, you can create new molecules with new functions, and it should be very, very original. So during the course of the synthetic studies on the oxidative reaction, development of the oxidative reaction of this diamine compounds, firstly, we expected that the oxidation should close the link here, but the student said one day, we can obtain this diode Harrison exactly, but it's a minor product. The major product was this one, dibenzo octane in 28%. Yeah, I was very amazed to see this because this reaction involves the CC bond cleavage between the bi-naphthalene unit as well as the nitrogen migration here. So it's a very, very new rearrangement reaction. So to synthesize other conjugated compounds, usually people use condensation, classical condensation reactions. For example, these very nice examples. So starting from benzene and diketone, obtain such kind of charging for high conjugated systems, and when you treat aromatic diamine with such that you can fuse oxidatively fuse aromatic diamine with this linked with other colors. However, such U-shaped or other high conjugated systems are very difficult to synthesize by conventional method. Here is the only example that can use this divergent energy and HAI as a major product. However, in this case, you you need to use alpha and beta amino naphthalene as an including more amounts. Also, the product is produced as a mixture still isolate. That is very difficult to prepare separate by chromatography. So here shows the summary of the screening of the reaction conditions. As you can see, when we use oxidant that contain iodine, only this dibenzophenone compound was obtained in high yield. Without these byproducts, will not form. So this reaction is general in terms of the other amino compounds. As you can see, you can introduce a dibromo substrate here, and also here, and also you can prepare the U-shaped highly conjugated systems that cannot be accessed by operational system. So we also demonstrated that this dibromophenoxy compound can be utilized for the access to the functionalized dibenzophenone compounds by paradigm catalyzed reactions or bacteria. So and this compound is a very beautiful trainer structure, and the column stacks like this. And between the columns, there should be the hydrogen bond between the H and N that might align the columns. And also they are emitted in solution and solid state. Especially when you put the donor systems in the high conjugated systems, the emission properties can be changed to the, from the pipettes type to the charge transfer type, shown like this. And they are also good. They have good electron accepting abilities, like ALQ3 that can be utilized for the electron accepting or transporting materials devices. So based on these findings and the collaboration with that guy, yeah. So the combination of the chemistry and the physics is very powerful strategy to create new molecules. So based on the new reactions, we can create new materials. Very powerful combination. So we designed a highly twisted, more highly twisted automatic systems as a TADF materials. So that's showing the strong intermolecular charge transport nature and the TADF properties. So here shows the DFT calculations. So as you can see, so depending on the donors you introduce, the twisted angles change from 33 to 83 degrees Celsius, 83 degrees, especially in the phenoxizing donors case. The DAD systems almost on the perpendicular system. So showing, meaning that in that case, the effective charge transfer should be very. So as I showed you, the starting from this type of energy, paradigm catalyzed reaction with aromatic diamines gave these compounds being good to high yields. And these compounds also showed a very high thermal stability. For example, the decomposition on temperatures is over 400 degrees Celsius. That can tolerate the evaporation through the manipulation of the materials, fabrication or devices. So civic experiments showed a very nice reversible curves, as shown here. And when compared to the acceptor unit and the donor itself, as you can see, in the oxidation process, that affects the oxidation level of the donor, and while the electron accepting process, it affects the electron accepting level of the acceptor. So, meaning that this in these systems, HOMO and LUMO decoupling is operating very effective. So, here shows the physics. In this carbazole on the diphenyl or amino compound, as the variety of the solvent increased, the strike rate was observed, showing that the mixing of local excited state and the transfer state in the polar solvent. However, in the this compound, the blue shift of the absorption edge was observed, probably meaning that this transition is a stir chapter. So, okay. Then, when you see the transient decay of DAD compounds in Xeonix film, as you can see, in the case of these compounds, as the time goes for the phosphorescence and the decfluorescence was observed as a mixture of these two components. However, in the case of these perpendicular systems, the delayed fluorescence was distinctly observed. So, probably the details of the excited state of these compound would be given by Andy. I don't know, but yeah. So in the case of these compounds, so as the time goes, the strike rate shift was observed, showing that the molecular rearrangement goes as the time goes. You know, the perfectly perpendicular systems is formed in this time scale. So here shows the effect of host materials. The host materials use many big influence on the singlet state and triplet state, especially in the case of this compound. The delta EST was as low as 10.2 at the board. When compared to this compound, this compound showed a big impact by the host material offsetting. So, meaning that you can control or manage the delta EST by selecting the host materials. Okay, so from the physical properties at the room temperature and low temperature, we found that the triplet state comes from this acceptor unit shown here. So as you can see, the spectra at the 80 Kelvin of the diamond energy is very similar to this compound, meaning that in these cases the locally excited state of the triplet state comes from the acceptor unit in these cases. Probably the donor and acceptor units are decoupled in like this also, meaning that there is almost no conjugation between the donor and acceptor in the structure. Okay, so when you heated up the compound, the TADF turned on right here and here, and in the case of this compound, the kinked octave was observed, meaning that other deactivation process or study at this point. But in the case of POZ, that should stabilize the charge transfer state of the compound. There was no kinked curve anymore, and we could observe the beautiful tunnel spectral and the activation energy of the was 98 volt. So to show the illustrative diagram of the excitation decay of this compound, here shows. So once the cigarette state is generated, the photon-induced charge electron transfer or something to give the charge transfer state of the cigarette state, and then between the charge transfer state and the locally excited state, the ISC and the RISC process lots of gas-free and effect-free. So you can obtain the TADF from the state. So this process should be controlled also with the spin of its charge transfer on IC. So as reported by their group, the intersystem processing is most effectively at the right angle between the donor and acceptor system. So meaning that indeed this compound system, the perpendicular donor acceptor donor system gives such effective intersystem processing. So recently, they reported the system similar like this. So he also showed the system very similar. So in their system, the locally excited state of the donor and the CD1 state is coupled. So meaning that our system is a complementary system of them. So donor acceptor or acceptor donor. It's a very So using this material, we fabricated all the devices, and as you can see, the device showed good EQV up to 60% and from the green to red, orange to red emission. Especially when you use electron donor hot material, the effective exciteplex formation was observed to show light in NIR region. And this device showed 5%, about 5% external contact efficiency, which is rather high as a TADF test or NIR anything for OLED devices. Okay. So here shows the energy level. So Professor Adachi also reported the exciteplex formation between this host material and the electron accepting negative materials. So from the estimation of the energy level, the exciteplex level is 1.199 volt. So here is a summary of this talk. Okay, so finally I have to write up our group. This picture was taken last December, and also